Today's goal is to solve advanced radical equations algebraically, meaning not graphically. Well, what makes some radical equations advanced? Some of the squaring techniques that come in and some of the strategy that you have to iterate. So for example, in example 1, if you square this expression, well, this is easy. Squaring and taking the square root are inverse operations, so they undo each other. So that is to say they sort of cancel each other out. So you just get x minus 3. But if you square 5 times the square root of x minus 3, that means you're multiplying 5 root x minus 3 by itself. And you notice multiplying 5 by itself, of course, is 25. Squaring square root of x minus 3 is x minus 3. So you get 25 times x minus 3, or 25x minus 75. Either of these is a correct expansion. What if you were squaring 5 plus the square root of x minus 3? Well, to square this is a binomial. It's two terms that are being added. And when you are squaring two terms that are being added or subtracted, you need the box method. So we have 5 plus root x minus 3 times 5 plus root x minus 3. 5 times 5, of course, is 25. 5 times square root x minus 3 is 5 root x minus 3. And so we have that term appearing twice. And root x minus 3 times root x minus 3 is just x minus 3. If we're combining our like terms, 5 root x minus 3 plus 5 root x minus 3 gives you 10 root x minus 3. So we'd have 25 plus 10 root x minus 3 plus x minus 3. Oh, well, now I have a couple more like terms. So this would be 22 plus 10 root x minus 3 plus x. Okay, that's one way that this lesson is a little bit more advanced than just solving basic radical equations. The other way that these equations are a little more advanced is sometimes you have to iterate or repeat a process. In this case, anytime you're solving an equation with radicals in it, you want to start by isolating one of the radicals, doesn't matter which one. So I'm going to add root x plus 6 to both sides. You want to isolate it except possibly a coefficient. If there's a number out in front, that's not a big deal. And isolating a radical is a good idea because then you can square both sides. And this works out nicely. You end up with just 2x minus 5 on the left. On the right, we'll need to use the box method. So we have 4 plus 2 root x plus 6 plus 2 root x plus 6 gives you 4 root x plus 6 plus x plus 6. Okay, we're going to repeat that strategy again. We got rid of one of the radicals, but our equation is still radical. It still has a square root in it. So we're going to isolate one of the radicals except possibly a coefficient. Before we do that, I notice that I've got a couple of like terms over here, so let's go ahead and add them. Now let's isolate the root. And now if I wanted to divide everything by 4, I can. I don't love dealing with fractions like negative 15/4, that looks kind of nasty. So what I mean by isolate except possibly a coefficient is that 4 out in front of the root, it's not really bothering me. We can go ahead and square both sides. Now using the box method on the left, we get this. And 4 root x plus 6 squared means we're multiplying 4 root x plus 6 by itself. I'm writing it out twice to help me see. 4 times 4 is going to give me 16. So 16 times x plus 6. And voila, you've just taken a radical equation and turned it into a quadratic equation, which of course you solve by getting all the terms on one side of the equation. That is, you want it to equal 0. And then if you can factor it, that'd be nice. If you can't, you'll have to use the quadratic formula. Now again, when you're solving rational equations and radical equations, before you hastily box in these what appear to be solutions, you must check for extraneous solutions. Unlike rationals, you're not substituting into a denominator, you're substituting into the original equation. So we'll have 2 times 43 minus 5 minus root 43 plus 6. And we want to know, is that equal to 2? Square root of 81 minus square root of 49 would be 9 minus 7, which is indeed 2. Okay, so 43 is a solution. Good. And over here, we've got root of 6, so root 1 minus root 9 equals maybe 2. We've got 1 minus 3. Well, 1 minus 3 is negative 2, right? We're assuming that when we check for extraneous solutions, we're assuming we're only taking the positive roots. So 1 minus 3 is not equal to 2, so this is an extraneous solution, and we conclude the only solution is x equals 43. Let's do one more just to really hone in on this process. Is it true that there are no solutions? No solutions would mean absolutely nothing works. So, I don't know, let's try solving it and see what happens. We're going to isolate a root, except possibly a coefficient. In this case, both roots have the coefficient 1, so that makes it a little bit easier. We're squaring a binomial, so we need to use the box method. Here we got a negative times a negative gives me a positive 1x. So we have 36 minus 12 root x plus x. Again, we need to isolate the root, except possibly that coefficient of negative 12. It's sort of a judgment call. For example, in this case, you can square both sides here. You end up with, big numbers. I don't know what the square root of 24 is offhand, but I do know if I divide both sides by the coefficient this time, it's really easy to solve from here. Before I box it in, let's just double check by substituting the possible solution into the original equation. Good, it worked. So this is my solution. Ooh, but the question didn't ask me to solve it. It asked, is it true that there are no solutions? No. The equation has one solution, x equals 4. It doesn't have no solutions. That would imply no values work, and we've just shown that when you substitute 4 into the original equation is satisfied.